All right, welcome back. In the previous video, we started looking at the HuggingFace Diffusion Models course and ran through the material for the introduction. So in today's video, we're just going to do the same thing for the second unit, Fine-Tuning and Guidance. So like before, I'll spend a bit of time introducing the concepts from the base material, and then we're going to dive into the notebooks, run through them at a leisurely pace, and see if we can bring up any interesting commentary or play with the code a little bit to help add some context if you're the kind of person who likes to have these video walkthroughs rather than just reading the text yourself. So as always, make sure you sign up for the course if you want to get updated when there's new units out, which we should have a few more early next year. So the point of today's lesson is to look at fine-tuning, guidance, and conditioning. And so in the previous one, we said, what are diffusion models? How do we train a diffusion model from scratch? And that's all well and good. But we said, okay, training from scratch is really time consuming, especially as you're working at higher resolutions, larger images, and you're wanting to get to higher quality. That can take ages. You're talking like days and days of GPU time. So we have the solution, which is to start with a model that's already been trained. It's already learned a lot about how to denoise images, and then you just fine tune that on new data. And this can be related data, like so if you take a model that's trained on faces and you train it on some slightly different faces, that's an ideal use case for fine tuning. But you can also totally do one trained on something in a completely different domain. So this example here is a model that was trained on bedroom images. And you can see if you squint, this still has the rough shape of maybe a bed and a bedside table. You know, some of these look vaguely bedroomy, but it's been retrained on the WikiArt dataset, which is images of old fine art. And so this kind of like adaptation works surprisingly well. It doesn't take long at all to get a good model because you're starting from a baseline that already has, like I said, lots of information built in. So it might be fun to go check that out. Okay, so that's like giving us better models faster by starting from an existing pre-trained model. And then the other thing that we're covering in today's notebook is how do we add control to what we generate. So if I take this model, it can generate these arbitrary sort of artsy outputs. But what if I want a specific color or a specific shape or a specific concept? How do I do that? And so there's a couple of ways. One that's really nice is guidance, because we can use existing models that have, a lack of control, and we can add in guidance at sampling time to steer the model with some additional conditions. So we'll see that in action. And then the other, which is in the sort of second demo notebook, is this idea of conditioning, where we tell the model explicitly what we'd like to generate. And during training, we feed in that conditioning information as extra inputs to the model to help it do its denoising more efficiently. And so then we can say, generate this specific type of digit or this specific type of image. And you can do that with class labels, or you can do that with text. And that's how we'll get text to image models later. Okay, so feel free to follow along. We're going to spend most of the time in this fine-tuning and guidance notebook. And then we'll do a quick little look at the class conditioning example, but that's very similar to the from scratch example last time. Just a little mini demo to show the idea rather than something sort of production ready or what you do, whereas the fine-tuning and guidance notebook is going to be focusing on how do we actually do some of these techniques with the diffusers library. So bear with me as my slow internet loads the notebooks and runs them. And we're going to be working in both of those notebooks, the class conditioned diffusion model example and this fine-tuning and guidance one. And you can run these on whatever platform you'd like. If you'd prefer to run on Kaggle or Paperspace, that's also fine. These links should just work. But do make sure that you have something with a GPU for especially the fine-tuning, just because otherwise, you are going to find that that's too slow to be particularly useful. Okay, well, this is taking so long to load. Maybe let's begin with a quick look at class conditioning, because the two are somewhat independent. And so we're going to do, again, just using the MNIST dataset, a very simple, let's run this anyway, a very simple example. And we're going to be using the diffusers, unit, and scheduler and things. In the previous from scratch one, we built our own. But in this one, we'll build on those pieces. But we're also going to try and adapt the model to take in some additional conditioning information. And so while this connects, just for fun, let's also try this with the fashion MNIST dataset. I'm not sure how this will work, but it should be a drop-in replacement, and we'll see how good the quality we get. I'll also make sure to try and show you the outputs from the previous run on MNIST. so that it's not too confusing. So these data sets are both, it's 28 by 28 pixel grayscale images. This is like as simple of a test set as we can get that's still going to let us try out these ideas and see them in practice. And so unlike the MNIST digits, the fashion MNIST dataset is going to be these photographs of different categories of fashion items, shoes and jumpers and pants and bags and so on. Okay, so we have our unit. It takes in a noisy image and a time step, and it produces a prediction for the noise. We would like to feed in some additional information, specifically the label of the image. So what we're going to do is we're going to take our standard unit 2D model, and we're going to create like a wrapper around that feeds in. So we're going to create our unit with additional input channels. So instead of a single channel input for our grayscale image, we're now going to have multiple input channels, one of which will be the image, and the others will encode that class information. And the way we'll do that is we'll have a learned embedding that's going to map our class label to some short vector, maybe like a 4-dimensional vector, just because this is only a small 10 class example. And then we're going to concatenate that on to our input. So given one channel input, we're going to then stack on like 4 additional channels, and those channels are going to encode the class embedding. So we can see that in code we have an embedding layer that maps from the number of classes to the class embedding size, which is from 10 to 4 if you're just using the defaults. And so our input channels to our unit is going to be 1 for the image, plus the number of class embeddings. And so if you were doing 3-channel images, RGB, it would be 3 plus whatever your class embedding size is. And then we're going to have just one output channel because it's still just producing its prediction. And then in the forward method, we're going to take in our noisy input X, our time step T, and the class labels. That's our conditioning information. That's this additional information that we're feeding into the unit. And we're going to reshape that. We're going to concatenate it with the noisy image X, and then we're going to feed that in along with the time step to our internal unit model. Right? So this is just one of the many ways that you can do conditioning. If you look at something like Stable Diffusion, they don't concatenate anything onto the input. They feed it in at these different layers. And in fact, if you look at the way that these unit models do the time step conditioning, they also do have an embedding, but they don't just feed it into the input layer. Instead, they project it down and add it to the outputs of various res blocks within the unit. So there's different ways that you can feed in that conditioning. But this is as simple as an example as I can make, and it still means the model has access to that because it can look at those 3 channels of the input, and from that it can use that information to know what class it's dealing with. So our training is going to look very much like the vanilla training we saw last week. Setting up our data loader, we're going to be training for 10 epochs, creating our class conditioned unit, and then the only difference here is that as we run through our data, we get some initial data, we create a noisy version of our clean input images, and then when we get our model prediction, we're feeding in our noisy X, our time steps, and our conditioning information Y. That's the labels, what class of fashion data am I doing. And so this might take a little while to run, but it's going to train. Let's just do it for 3 epochs here. Our images probably won't be amazing, but that's fine. And you can explore all of those parameters as well. But you can see here now during sampling, we're starting from a random input for our X, but as our conditioning, we're feeding in 0, 1, 2, 3, 4, 5, 6, 7, getting a number of examples of each. And then we're just calling our prediction with those desired labels Y. So that's like our target. We'd like to generate these digits. And when we do that, sure enough, that's exactly what we get. We get the digit 0 for the first, 8, the digit 1 for the next 8, and so on. And you can see it does a pretty passable job at generating those digits. So that's pretty nice. Okay, I must have forgotten to change my runtime type to GPU. So we're not actually going to run this because that would take way too long, and I'm not going to restart either. You can see the examples here look pretty nice. I do encourage you to try it out with Fashion MNIST, see what they look like. Tweak the learning rate, the batch size, the number of epochs. Can you get good looking fashion images? I will leave that as an exercise to the reader since I forgot to change that runtime type. But for now, what I'm going to do instead is just shut the session down, terminate, and let's go over to the Fintuning and Guidance notebook where we're going to spend the bulk of our time today. So remember, we're looking at 3 different methods for adding control. Well, we're adding fine-tuning to train it on new data. We're adding guidance to steer it at inference time. And we've just looked at conditioning, which is actually giving the model explicitly a target for what you'd like to generate. So we've done the conditioning. Let's now do fine-tuning and guidance. So in this notebook, we're going to first of all look at ways of sampling. so that we can speed up our iteration time when we're testing things. And we don't want to be sampling. Remember last time, a full 1,000 steps took a very long time, so we want to speed that up. Then we'll fine-tune an existing model on new data. And I'll do a little diversion just showing how you can log examples to weights and biases or elsewhere so that you can see what's going on, because fine-tuning tends to be not super easy to see what's happening in the loss, but it's very visually apparent how well the model's doing. And then finally, we'll do some guidance. As always, if you have questions even after this video, feel free to put them in the comments or on the Diffusion Models class channel on Discord. Okay, so this time I'm going to make sure we are running on the GPU. Don't want to make that same mistake again. And we'll install some libraries and also make sure that we are logged into our HuggingFace account so that we can save our trained models to the hub, and so that we can also share them with other people and see them in action there. Oh, and one of the other things we'll do is we'll show how you can make a demo for your trained model using Gradio at the end. Okay, so while that runs, I'm going to open my HuggingFace account. Well, I'll wait for the prompt here actually. Shouldn't take too long. And you don't have to do this login step if you just want to run the notebook, but I would encourage it. It's nice to have these artifacts from your training, the saved models and also the weights and biases runs. It's nice to have them saved in the cloud elsewhere for people to access, and to have them as a permanent record. And then it means you don't have to retrain them every time you want to do the examples. You can just load them from the hub and continue. So very, very useful. Whoops, why didn't that copy? Copy. Okay, my copy buffer is not working. I don't know what the deal is there. Strange. I have just rebooted my computer. Anyway, well, we won't push our models to the hub in this example walkthrough, but you really should do that if you want to save yours. Okay, so we're loading some libraries. We are loading the DDPM pipeline and also this DDIM scheduler, which we'll look at first. Okay, so to start with, we're going to load a pre-trained model. And this is a model trained on faces. You can go and look on the hub, search for this exact model. In fact, let's do that. huggingface.co/Google DDPM, and we'll see some background on the model, what paper it's from. This is from the DDPM paper, uploaded by the Google organization, which is nice. And so if we run the model, right, we run it like a function. We're running the call method, which you can go and read, by the way, just link to the code there. And this is going to go and generate the image. So it's going to run through, let's see here, for ion scheduler.timesteps. It's going to get the prediction, compute the next one, and it's starting from a random starting point. And then it's going to display it. So we can run this. It is going to take a little while because it's doing, like I said, 1,000 steps. And so the first thing we're going to do before we go through the rest of this notebook is figure out how we can sample in fewer steps, so that we don't have to wait 2 whole minutes every single time. And so what we're going to do is load a different sampling pipeline. And this one is the DDIM pipeline from, I think I linked to the paper here, Denoising Diffusion Implicit Models. So again, you can go look at that paper. Sometimes the papers can be a bit technical and confusing, but the core idea here is that we are taking larger steps. So instead of taking 1,000 small steps, moving a little bit based on the model prediction, adding a bit of noise, moving a bit, adding a bit of noise, moving a bit, adding a bit of noise, the DDIM sampler is going to take just say 50 much larger steps. And we can also set whether we want to add additional randomness into that or not using this parameter called eta, and we won't by default. So there goes my electricity, and therefore my network connection. So just give me a second. What I'll do is won't abandon this. I will abandon this video. Okay, I've lost my electricity, but our long sampling loop is finished running. I've reconnected on mobile data, so we're going to forge ahead because I don't feel like re-recording that whole intro. All right, so we're going to load this new scheduler. And the nice thing is, if we use the from pre-train method and point it to the same repository that we used to load our pipeline, we can then hopefully just use this. It's going to load the same settings. It's going to look at the scheduler settings for that pipeline. Because if we go pipe.scheduler, you'll see this has the specific settings used. What do I call it? Pipeline, maybe. Image pipe. It has the settings that we use during training for beta start, beta end, the type of scale, the number of steps, etc. And so if we load from pre-trained, it's going to have those same settings. But we can see now, instead of having 1,000 time steps, we are going to set our number of inference steps to only 40. And so now the scheduler is starting at noise level equivalent to the original time step 975, then jumping to 950, 925, and so on. So it's making a much larger update each time. And so we can write a sampling loop with the scheduler. We're going to start with some random images, and then we're going to loop through these 40 time steps. So much shorter than the 1,000. We will prepare our model input, get our noise prediction, calculate the next one using the scheduler.step, and that's going to do that work of figuring out how big of a jump to make. And then we can also store, in this case, the predicted original sample for each step. Like what does the completely denoised image look like according to the model at that point, and what is the next step looking like. And so if we run this, you're going to see that at the beginning, this is our noisy input. The model's predictions are pretty bad, right? But after 10 steps, the updates haven't been that big yet, right? It's been making small adjustments based on the predictions, but it's now at a point where the predicted denoised images look a lot better. Still very blurry though. By step 20 and 30, the details have started to come in and show, until by the end of the process, our images are nice and crisp and done, and it's completely denoised. And so on the left here, this is like the actual process as it's running. And on the right, these are the predictions given this current input. And so it's not denoising this completely, it's only updating it a small amount each step. But you can see how the current value of X is getting less and less noisy, and the predictions are getting more and more refined over time. So that, at least for me, helps internalize what's happening in each schedule. In each step of the scheduler, like if you go and look at the method, let's uncomment this and watch it, you'll see that it's calculating that completely predicted denoised image. So here, it's got some good explanations of the notations and things, calculating those scaling factors, the noise schedule. Here we go. So scheduler.step. So it knows what time step it's working on. So it's going to calculate the predicted original sample, which, since we're predicting the noise, is going to be the current sample minus some scaled version of the model's prediction for the noise, and then scaling that accordingly. So that's giving us this predicted original sample on the right. And then to make our update for the current step, we are going to do previous sample. We're calculating a direction, which is pointing towards the model prediction. Previous sample is equal to some scaling times the original sample, plus some amount in this direction of the model prediction. And then if ETA or eta is larger than 0, we're optionally going to add some additional noise in. But I think by default it's set to 0. Okay, so we have this much faster scheduler. This is really nice. We can now replace the pipeline's original scheduler with this new one and call the image pipe's forward method with num inference steps equals 40. And now our pipeline is generating an image, but in 40 steps rather than 1,000. It still looks pretty good. Okay, so this is like our preliminary work, just so that we can iterate faster and we don't have to wait for the full 1,000 steps each time. This is going to dramatically speed things up as we get to especially the guidance section. Now for the fun bit. We've got this pre-trained pipeline. How do we retrain the model on new training data? So it turns out that the training process looks pretty much identical to training from scratch, except that we start with the existing model, right? So you can see it in action. And what I've done is we're going to load this data of butterflies, same one that we used in Unit 1. And even though this is very different to faces, you'll see we can have some fun training for a little bit on these butterflies, starting from the face image. If you want, you could try vintage faces or anime faces as something closer to the original training data domain. But this is just a fun little demo. And what we're going to do is, in this notebook, we have kind of the simplified training loop, but there is also an official training example, which I suggest you look at and maybe modify to start from a pre-trained network, because it has things like accelerate and all of these other kind of conveniences and improvements to our basic training loop. Okay, so a few things to note. We're loading our images at size 256. And that means that we can only work with a relatively small batch size if we don't want to run out of GPU. So that's going to have to be something that we work with. And then in the training loop, we are just setting the optimization target to be the unit of this existing pipeline. So we're going to be updating this unit based on our training. So setting up our settings, setting up our optimizer for epoch and range epochs for batching the data, get our clean images, add some noise according to random time step, get the model prediction, compare it with the actual noise, store the loss, loss.backwards, optimizer.step, all pretty similar to before. And now you'll see this loss is really noisy, right? Because the loss dramatically depends on what time steps we're using, and we're picking those at random. If it's a low time step, it's quite an easy prediction. If it's a high time step, maybe not so easy. But it's very hard to see if this model is improving at all. So that's one consideration to take into account. The other is that we're working with these really small batches, and that means we have this noisy signal, and we're trying to optimize with it, and that's not ideal. So you'll notice when I said optimizer.step, there's actually a line of code here that's only applying this update, step and 0 grad, if the step counter modulo this gradient accumulation steps is 0. So what we're doing is every batch of the data, we're feeding it through the model and getting the predictions and calculating the loss and storing the gradients, loss.backwards. But unless we call optimizer.step and optimizer.0 grad, the next time we call loss.backwards, it's not going to erase the previous gradients, it's just going to add to them. So this is called gradient accumulation. And so that's why we have this trick. We have gradient accumulation steps equals 2 here, and you could change this to something else. And when we run this, what it's going to do is it's only going to update the parameters once 4 batches have been passed through the model, using the gradients that are the combined gradients from those 4 batches. So this is kind of equivalent to having a batch size of 16, right? Which is nice because that gives us a stronger update signal, a less noisy gradient. But we're only working with one batch of 4 images at a time still. And so we're not worried about running out of GPU RAM. You can see even with a batch of 4, my GPU RAM is pretty close to full. And so this gradient accumulation trick is a nice addition. And we're doing it manually here to show that it's relatively simple. Now there's considerations that you want, because by changing the effective batch size, you probably want to change the learning rate accordingly and so on. And so if you look at the Accelerate docs, you can see how that will handle all of that for you. And if you look at the official training script, you'll see that they have Accelerate and all these other things to handle that kind of addition like gradient accumulation for you. But still, it's kind of nice to have it all sort of explicitly out for ourselves to see. And so I'm going to stop that there. The other thing is, we're printing out the loss every epoch, and we saw that noisy loss graph. Neither of those are super informative. And so the other thing that I like to do is to say, okay, maybe this is not ideal to be training in a notebook and to be watching this kind of very low information signal as I'm training, and I'm waiting, in some cases hours to finish these epochs of training. So what I've done is I've written a little script, and this is a very lightly modified version of that training loop. We're loading our pipeline, loading our data sets, running through that same training loop. But you can see here I've added just 1db.log loss.item, right? So instead of just storing the losses in a list, I'm also logging them to weights and biases. And then occasionally, every number of steps, I'm going to do a sampling loop and save the resulting image, right? So not that much addition to the base loop. And then I've got 1db.finish at the end, 1db.init up at the top, right? Telling it what project and so on I want. And then this is all wrapped in a function that takes a number of arguments. And I've used the call pass decorator from fastcall, from fastcall.script, import call pass. This will turn this into a nice command line script. And so now what I can do if I want to run this code is I can run it like a, we'll see this just now actually. I can run it like a script. It'll log to weights and biases, and then we get, let's look at the logs from that training run. We get this nice dashboard that updates in real time as that training script is running, where we can watch the updates. We can see what the generated images look like, and we can see what the loss is doing. And this to me is a really nice way to keep track of how the fine-tuning is going. Maybe you also save your model every few epochs, and so that you can decide, okay, it looks like it's trained enough. I'm going to stop the training early, save the model weights. That's great. So this one here, when it started, the images looked very much like the training set. Although even after 250 iterations, they were slightly different to the original bedrooms. But you can see, okay, yeah, this is the demo that I showed in the intro. But as we train for longer, they get less and less like the training data that the model was originally trained on. And we get more and more sort of like nice, diverse, artsy looking samples. So I quite like this. Yeah, you don't have to use this obviously, but you can get the loss graph, you can edit it and view it and transform it in all sorts of interesting ways. So yeah, that's just a little glimpse at like how I like to do this kind of training rather than just running it all in a notebook. It's good to have, yeah, this kind of thing. So there's commented out code at the end of the notebook for running the script, right? Like, so if you run down to the bottom here, I think I still have it at the end. Oh, that might be a typo. I think we actually moved it up higher. Excuse me. Oh yeah, here we go. So if you want to run this, you can see because I have that call pass decorator, I can run it with these command line arguments, and those are going to be passed as inputs to the fine-tuned model scripts like main function. So that's pretty nice. Yeah, so we have an example of running that script if you'd like to do that. What you can also do is take these same ideas and go and modify the official training example from Unit 1. Let me see if I link to it here. Or go back to Unit 1 and find it. To see if you can add that kind of logging and to see if you can start from a pre-trained pipeline. Because that script from Unit 1, the official Hugging Face training example, has a lot more bells and whistles like accelerate and so on for training on multiple GPUs or for handling gradient acceleration, all that kind of stuff. Anyway, once we've done our training, this is with the butterfly one, which we haven't actually done. And if you haven't run the training yourself, you can also skip that and instead load the model, which I think we do shortly. Okay, we're going to load a different one that I've trained anyway. So you can save your model once you've done this fine-tuning. ImagePipe.save pre-trained. That's going to save it to a folder just like we saw in Unit 1 that has a folder for the scheduler with the configuration files and so on, and a folder for the UNet with the PyTorch model.bin, the actual raw weights of the one, and we can also push that to the hub. So this code here is going to give it this name, right? Which is, in this case, the example was training on butterflies for 2 epochs, starting from this model. Give it a path to the folder where we saved it. Give it a description. If you run that, that'll upload to the hub, and then you can load it later. So we're going to use a model that I trained, the one whose logs we were looking at, trained on WikiArt, starting from the bedrooms model. And we're going to sample from that just to check that it's all working. And this is the model that we'll use for the rest of this notebook for the exercises on guidance and things. You can also use your existing model if you fine-tuned one using the code above or using the script. By all means, use that instead of mine. But this is going to give us a nice consistent starting point. It's a model that's been fine-tuned for a little bit on new data. And then we're going to see like, okay, how do we add some additional control? Because you'll see once we generate with this, we get some images that look kind of cool and arty, but we have absolutely no control over anything as to how they actually look. And so that's going to be the next section, is how do we add guidance? Well, as samples, final consideration with this fine-tuning thing, like I sort of mentioned earlier, it can be tricky to tell how well it's working, right? If you're fine-tuning an existing big model on a small data set, maybe you want it to stay almost exactly like the original model, but you're just adding a little bit of extra information or skewing it in some direction. So in that case, you probably want a fairly low learning rate, maybe using something like exponential model averaging, EMA, again, something that's available in the official training script. There's this great blog post about tuning Stable Diffusion on Pokemon images. But in a different situation like this, we want to basically retrain the bedroom model on WikiArt. We want to be able to generate completely new data. And so having a larger learning rate and training for a bit longer, I trained it for about an hour, makes sense. And so the loss plot doesn't show us much improvement, but if you look at those examples, you could see we were quite quickly starting to get the kinds of images I was hoping for with my particular like artistic intent in this case. And of course, if you want further real faces, you're going to have to tweak the settings and go in a different direction. But this is what I wanted. And so, yeah, just to say, fine-tuning is very much still a bit of an art rather than a hard science. Anyway, so you've got a model loaded. We can generate some arbitrary images with it. That's great, using our DDIM scheduler. That's all well and good, but how do we control what's going on here? So that's the final topic of today's video and this unit, and that's guidance, right? We didn't train this model with any kind of conditioning, so we can't tell it what to generate explicitly. But what we can do is add a function that defines like how well does the image, how good does it look according to some criteria, right? And so for this example here, what we're going to do is you're going to create a loss that compares the image to some target color, right? And by default, that target color is a sort of light teal. So I'm going to get my target color. I'm going to map it from, it's by default like RGB between 0 and 1. I want it to be between -1 and 1 to match the images. I'm going to reshape it to work with the size of the images themselves. And then I'm just doing images minus target and taking the average of that. So this is like the mean absolute difference between the image pixels and my target color. And so this is me expressing something about what I'd like the images to look like. I'd like them to be as close as possible to this target color. So now we're going to modify that sampling loop. And at every step, we're going to set requires grad equals true on X. So we're going to start tracking gradients related to this X. We're going to calculate the denoised version. And then we're going to evaluate this denoised version using our loss function. How well does this denoised version match our desired target, right? Is it the right color? Is it the right shape? Whatever your loss is. And we're going to find the gradient of this loss with respect to X. In other words, we're asking, how should I change X such that the denoised version better satisfies my criteria? And we'll use this gradient to modify X before we step with the scheduler, pushing it in a direction that hopefully gives us images that do in fact match that. And so this is what it looks like in code. Same sampling loop as before, prepare the model inputs, get the prediction, but now we're setting requires grad equals true. We're getting the predicted X0, and we're calculating our loss, optionally with some kind of guidance scale to emphasize it more or less strongly. We're finding the gradient of the loss with respect to X, and we're modifying X. There's a minus sign there, so we're like pushing it in the direction that hopefully minimizes this loss before we step. And so you can see this is the loss just printing out every 10 iterations. What is that guidance loss? Starts out pretty high and drops down. So the original predicted denoised images didn't really satisfy that criteria very well, but over time they've gotten better and better. And you can see instead of the random outputs here, we've now pushed them such that the outputs still look kind of arty, but they all match our target color, right? So that's pretty neat. Now, there's something worth noting here. There's two versions. The first one, we are getting our model predictions with torch.nograd, and then we're setting requires grad equals true. And so when we trace the gradients back, what we're doing is basically just going through this scheduler.step process, which is just like a very simple mathematical combination of the model prediction and X. So this is fine, but the gradients aren't necessarily accurate because we're saying, how do I modify X such that when I apply this denoising step, I get the right output? What we really want is, how do I modify X such that when I feed it through my model and do the denoising, I get the desired output? And so that's the difference here. We're setting requires grad equals true before we feed X through the model. And so now when we trace those gradients, we have to trace them back through the whole UNet. So it's more computationally expensive, but it gives us more accurate gradients because we're now updating X in such a way that when the model denoises it, rather than just using the existing model prediction, we get something that better matches our loss. So we have to work with a smaller batch size here, 4 instead of 8, and the GPU RAM requirements are still going to be higher in this second example. So you can choose which approach to take. I usually use this first one, even though it's less accurate, because oftentimes the loss calculation requires a lot of memory already, and so having like slightly less computationally intensive version is fine. But this is nice if you want even generally better results. So you can see here our loss is dropping. It hasn't dropped as low. So these outputs might not match the target as well, but that's something we can change just by increasing the scale. However, arguably, they look better than these ones, some of which are just almost like completely plain colors, right? These 4 or 5 ones aren't really looking like art at all. They just look like green, right? Because this approach is kind of crude compared to this one where we're still incorporating the model in that prediction path. And these, debatably look nicer. So you can choose which one you like. Try it. Let's try it with a different color. So we are saying our loss is equal to color loss. We can specify the target color. So let's go one that's mostly red. Very little green, maybe a bit more blue, so like a reddish purple. We can run that and see how we get. Yeah, and this is quite a fun thing to play with. Obviously, this color loss is kind of a contrived example, but you can imagine maybe a style loss, right? Taking inspiration from the old school style transfer methods to make your textures and style match one input image. And then maybe you have another loss that says how well does the overall structure, the content, or like a perceptual loss match a different image. Or you could imagine feeding in clip, right? The model that can measure similarity between text and images. You could use clip to guide this, and in fact we'll try that just now. Yeah, so there's lots of possibilities here with this kind of guidance. You could even train a separate model, and this is called discriminator guidance, to say how good does the generated image look? Does it look real or fake? Use that as a guidance function. There's a lovely paper on discriminator guidance for better sampling of diffusion models. But yeah, anyway, it's a pretty cool technique. Here we have our lovely pink outputs. And later on, I'll show you how you can wrap something like this in a Gradio demo to share this with other people, and how you can try out this particular model nice and quickly. Okay, so the final demo is going to be doing exactly what I mentioned. What if we would like to guide this with text rather than just the color? And so we're going to use Clip. Clip is a model from OpenAI that allows us to compare images and text. It was trained to associate images with text captions. I've written a little report on the OpenClip project, which has done some great work replicating Clip in the open and sharing the model weights and the details of how it was trained and so on. So you can go and check that out for a bit of background and some demos of what Clip can do, a bit of info on the training, interview with one of the people behind the recent training of the large open model. Yeah, so check that out if you want some more background. You can see it applied for classifying some different images. Yeah, so lots of reading there. There's also a lesson on the topic in my course, still in progress. But yeah, we're just going to load up Clip model and use it almost like a black box in the hope that we can use our Clip loss to measure the similarity between an image and a piece of text, right? And so I'll go ahead and run this. I should have done that before I started waffling. But then what we're going to do is now, very similar to the previous example, we're going to set up our sampling loop, but this time we have a prompt, right? And we can change this. So let's go blue painting of a coral reef, something like that. We are going to embed that prompt with Clip. That's going to give us our target like text features. We're going to start from random. You might want to lower this if you're running out of RAM. And in fact, let's do that. Let's just do 2 images for now. And then we're going to run through our scheduling process, getting the model input, making a model prediction. And then in this case, what I've chosen to do is take multiple versions of X, because let's see here, in my Clip loss, we have some augmentation. So we're going to apply some random transforms each time. This is just so that you're not just optimizing the same image input to Clip each time. It's nice to have a bit of variation. Yeah, so we're doing four cuts, or whatever you set n cuts to get a better signal. We're doing 4 slightly different versions of this. We're combining those gradients together, and then we're using that to do our update step. So let's run this, and then there's a couple of things I'll talk about. Hopefully, if you ran this with the default prompt, they look kind of like roses. We're running it here with this new prompt of a blue painting of a coral reef. So let's see how that goes. And it looks like it's going for 50 steps. Oh, okay. That doesn't look very corally at all. Might have to tweak this. Okay, so there's a few things that we can do here. One, you could try using the more accurate gradient version. That's probably a good idea. 2, we need to think a little bit about whether we want to apply our guidance mostly at the beginning, or mostly at the end, or some constant throughout. And so in this example here, I actually calculate this alpha bar, and then I use the square root of that to scale the conditioning gradient, right? And you can leave that out and see how that works. Let's just do like 30 steps. And this is not perfect. This is very fiddly. Part of it is we're only doing this kind of hacky Clip loss that I've coded up here. If you go and check out the official Clip guided diffusion space on HuggingFace, you'll see that they have a much more complicated way of taking the cutouts and calculating the clip loss over a number of cuts. Okay, yeah, vaguely coral reefy. Let's see if we can do something that's very recognizable. The other thing to remember here is that we are working with a very random model. It was trained on a little bit of wiki art after being trained on images of bedrooms. So expecting it to produce like flawless, high quality art is maybe a bit of a stretch. But this kind of clip-guided diffusion, using a better model that was trained on just like really well trained on unconditional image generation, that was actually like the way that people did, they did text to image for a while. Rivers Have Wings had a lovely clip-guided diffusion notebook. Maybe you remember disco diffusion. Yeah, so I mean, this looks like it needs a lot of tweaking. It's not perfect, but it's showing that in principle, at least, we can use some much more complicated loss function here to steer our generation. And I think that's pretty cool. So yeah, feel free to like try some of these different schedules perhaps, or go and look at the source code for the clip-guided diffusion example here. You'll see they have this make cutouts class for handling like picking different things. They have their loss function, additional loss functions, TV loss and range loss to try and make the images less noisy. And they have their inference code that's yeah, definitely a little bit more complicated than our tiny little demo. But you can see, okay, it's blue and wavish. Maybe the guidance scale is too high. Maybe we should add back that scaling. Yeah, so there's lots to experiment with there. And this, in its current iteration, is not something that you maybe need to use, but hopefully it gets the idea across. We have this really powerful way of adapting these models at inference time using this idea of guidance. So I think final thing before we wrap up, let's just show how you could make a demo. I really like Gradio, and it's really well supported on the HuggingFace Hub. Gradio is like a set of frameworks and components for making and sharing these ML demos. What we're going to do is wrap our generation function in a function that takes in some arguments, and then we can create a whole Gradio interface in a very few lines of code, specifying our inputs that the users are going to have control over, specifying what output we're going to have, and then creating our Gradio.interface, telling it what function to call, what the inputs and outputs are, and optionally specifying some examples. And if you launch this, you'll see something like this. In fact, we can go and see the actual space. And this is, yeah, a really neat way to say, okay, I have this process, right? Maybe it's color-guided wiki art diffusion. Maybe it's your own model that's just got a default sampling loop, but you want to show off your fine-tuned model. You can go and pick what settings you'd like, what types of inputs, and there's a whole library of, there we go, nice peachy pink. I can increase the guidance scale to get stronger adherence. Yeah, so go play with this thing, go give it a like, but also go make your own. If you check out the Gradio docs, they have tons and tons and tons of different components that you can use. So for example, you want to take in text, you want to take in a number as a slider or a true or false radio button. All the docs have good little examples showing you like how to do that with a number of inputs. You can see here, there we go, great, submit. Yeah, so it's really well documented. It's really easy. You can see the code for this is pretty minimal, just defining what our inputs and outputs should be and what function we'd like to call with those inputs to produce that output. So a very flexible framework, a very mini tutorial on it here. But I thought it was quite nice to encourage you to say, look, if you've built something cool, like we built something cool here, right? We can type in some text and we can get some images out. Like that's really nice. Wrap that in a Gradio app. You can go and either come across to my space, options duplicate this space, right? And then you'll get a duplicate and you can go and edit the different files, or you can create your own from scratch. So let's just check out what the files look like. We have a requirements.txt that specifies what libraries you need, and then we have app.py that is just wrapping all of the code that we need. So we're loading the pipeline, the scheduler, specifying our color loss, writing our generate function, specifying our inputs and outputs, and then wrapping that in a Gradio interface. Right, so really, really simple. You can come in and put your own pipeline here, and if that's the only modification you make, that's fine. But if you want to get really creative, maybe change to a different loss, generate a number of images or one image. Yeah, just have fun messing around. And if you want to create your own from scratch, you just go Options, New Space, and you can choose Gradio, and that'll set you up with everything you need. By default, it'll run on a CPU, but if you make something cool, or if you have a bit of money, you can rent a GPU, $50 per hour, or you can ask the Hugging Face team if it's something particularly cool, and they might give you a community grant to run your space on a GPU. So I hope you've enjoyed that. This has been Unit 2 of the Diffusion Model course. So in the next video, we'll look at Unit 3, which is going to be focused on Stable Diffusion. So going from like our ideas with diffusion models in general and some of these cool tricks like conditioning, how do we go from there to this amazingly powerful model where you can just type in exactly what you want, and it'll generate a fantastic image of that. So that's going to be in the next video. We'll be looking at this powerful, like kind of state-of-the-art open source image generating model. So stick around for that. I'll try and record it in the next day or two if I have time. So you should see that on this channel here. Otherwise, keep an eye out on the Hugging Face Discord. I'll put a little note in there as well. Thank you so much for watching.